predictive control. Okay, so what's done here is the best way to illustrate this is let's do a one-dimensional problem. Okay, so let's say that you are here. This is at present time. So let's say the present time is t0. So you are making a prediction. So let's say this is t horizon, or t prediction. T horizon is better. So over a certain amount of time, let's say 5 seconds in the future, you are trying to predict what's the best path is. So this is like your best path. Okay, how do you achieve this? Well, you need to solve an optimization problem. We've seen how to use f minimize, right, in SciPy. So you could do that. But then what you do is this. You don't try to use this. After, let's say here, when you reach at this time, t1, so you've taken that plan, you've implemented that plan. Here we have new information arrives to you because you have sensors which are on and they're taking more information. So at that time, this time, you have new information, new sensory information, and then what you do is you replan. This is your T new horizon. So you do a replanning, and your replanning might throw up a trajectory like this. Note that your new plan and the old plan were different, right? And that's because now that since you have new information, you can make a better plan. So this is a new plan, and then you keep doing that. You again take data here, new info, you make a new trajectory. Sorry, you will be, my bad. You should be right here. There's new info here. Then you make a new trajectory over here. And so on. So keep replanning. And the problem with this approach is that it can be very computationally heavy because every time you're solving optimization, but by making the problem simpler, usually people, what they do is they linearize it. You can actually solve this in real time. So I did the same thing. This problem, the motion planning problem with model predictive control. The difference with DWA, the one which I talked about, is that DWA basically does this rollouts. It does this various rollouts for different v omega and then finds the minimum. This one, what it does is actually calls minimize and does it. And I decided to just use the angular speed, but you could actually change v and omega. You could not only change v omega for a prediction horizon, you could have v omega at different time intervals instead of having one for the entire horizon. So I just took the simplest case. So here is MPC, a model predictive control. Okay, so essentially I would call MPC. It'll have the same inputs. I just decided to keep the velocity constant, and omega is what is set by MPC. The difference, as I said, was that there was a cost. The cost is very similar to the one which I have here. There's a term for going to the goal. There's a term for I used a different, I used this log cost, but you could also use 1 divided by the distance squared. And then essentially I call op.minimize. That's the difference between DWA. I call this minimization function. Okay, and it does the calculations for me. So I need to import SciPy optimize in order to do that. SciPy optimize. So let's do this without the same obstacles, but without using MPC, no obstacles. So that should be very straightforward for the optimizer, no obstacles. But the one which makes it hard actually with obstacles, you'll see that it actually slows down a bit. The computation takes more time. So what I do here in this case, it's not real time. It's basically doing all the computations and then doing the animation, right? So if you do this in real time, it'll actually, it could actually not work on the real system because In the real world, you don't have the luxury to stop and continue. You need to do the computation real time. So here you get a solution. It just takes a diversion. Now here you might see that it may or may not work when you add an obstacle. So here I'm adding another obstacle to the first one. And then the time just indicates that this is not, of course, I'm not implementing the real time. It's just doing it offline. So the calculations are taking time. It's ensuring that it works. Now here you see that it tries to go there, but then it takes off, and then it does a good job. You could also add more. So I think the last time I added 1.8, 1, 0.2. I don't know if this will work. We could try it out. Many of these methods, you require it to tune the cost function to get it to perform the way you want it to perform. Okay, so let's see if it works. Because that was smart. It took the left turn instead of the right turn.